Today we start a new module on characteristic times and lengths. At the end of this module you should be able to state the characteristic times and lengths associated with the following: the bulk carrier population under equilibrium, the relaxation of disturbance in the following: first, the carrier momentum and energy, then the excess electron hole pair concentration, and 3, the space charge. Then you should be able to state the characteristic time associated with the transit of an average carrier across the device length. You should be able to state the conditions including those at the boundary and the defining differential equation associated with each characteristic length and time. You should be able to state the order of magnitude of and factors governing the characteristic times and lengths. You should be able to state how the characteristic times and lengths are useful in qualitative description of device phenomena, simulation and characterization of devices, and validation of approximations. You should be able to derive the defining equations associated with the various characteristic times and lengths. You should be able to identify approximations which will simplify, decouple, or eliminate any of the equations of carrier transport, such as drift diffusion equations, balance equations, etc. And finally, you should be able to express the qualitative analysis using graphs of electron concentration, hole concentration, electron current density, hole current density, electric field, and potential versus distance and time. Now we shall be using the one dimensional analysis, and therefore only x coordinate is indicated here for the distance. Now to begin with, let us see what is the motivation for a discussion of characteristic lengths and times. Now suppose someone asked you the size of this classroom, you would probably tell the area in terms of square feet or square meters. You would not use a metric such as square centimeters. So suppose someone asked you the distance between this classroom and the marketplace, you would say that the distance would be in the order of, say, kilometers. On the other hand, if you are talking of the distance between various parts of galaxies, you can even use a metric such as millions of kilometers, right? Now similarly, about time, the duration of a lecture, it is in minutes. The duration of an end semester examination, you would answer the question in terms of hours. Duration of a semester, it would be in weeks, and so on. So in other words, you use different metrics of distance and time to describe different situations. So your mind automatically changes the metric, something like changing a gear when you accelerate a vehicle. Now similarly, in the context of modeling of semiconductor devices, the characteristic lengths and times are very, very important. They give you an idea of what kind of approximations are possible in a given situation. For example, look at this slide. Which was presented in the discussion of transport equations. So the limitations of various transport models are indicated here, and the red curves indicate the boundaries within which each of these method is valid or used. Now if we want to come if you want to understand how these boundaries are arrived at, then a discussion of characteristic lengths and times is very important. So you can see that in this graph, actually the y axis is characteristic length and x axis is characteristic time. So, towards the end of this module we will try to understand this graph which talks about the validity range of various models in terms of the various characteristic lengths and times that we shall discuss in the module. First, let us look at characteristic times and lengths associated with bulk carrier population in equilibrium. The picture in equilibrium is sketched here. So, this is an approximate picture where the scattering event is assumed to be instantaneous and localized. So, it is in terms of this picture that we shall define the various characteristic lengths and times. So, to begin with, let us talk about the root mean square or thermal velocity V thermal. So, this is nothing but the average speed of the electron at any temperature. Okay. So, we have already discussed how this average is arrived at. So, it is arrived at by squaring the speeds of each of the electrons, then taking the mean and then taking the root. The de Broglie wavelength of thermal average carrier. Now, an average carrier which has this velocity has a momentum given by effective mass multiplied by thermal velocity, and therefore, you can associate a de Broglie wavelength with this momentum given by this formula lambda thermal given by h by the momentum. As we will see, this de Broglie wavelength will enable us to decide whether the particle approximation of the electron or hole is valid in a situation or not. The mean free path between collisions is the average length AB. So, this between two scattering events. So, this length. On the other hand, the mean free time between collisions is the time required for the electron to traverse that average mean free path AB, and this is given by tau c equal to the mean free path, mean free length divided by the thermal speed. The minority carrier lifetime, that is the time between generation and recombination. So, look at the events shown here. This point here shows a electron hole pair generation. The electron is moving to the left and the hole is moving down. It undergoes various scattering mechanisms and then finally it finds an electron to recombine with. So, this is recombination. So, the time between this G and R is the lifetime. Since holes are minority carriers in n-type semiconductor, this is minority carrier lifetime. Now, evidently this time will be more than the mean free time between collisions, because the carrier is encountering several collisions, several scattering events before it recombines after it is generated. Now, similarly, there is also a majority carrier lifetime. However, we normally do not discuss the majority carrier lifetime very much, because in device phenomena it is a minority carrier lifetime that plays a role. Let us make some comments about derivation of characteristic time or length based on the drift diffusion model. We will have to follow a few guidelines, some steps to do this derivation. So, this is our drift diffusion model. 5 of these equations have been grouped together. Now, this is because these 5 equations are all coupled to each other. You can see this very easily. For example, this Jn appears in the equation for continuity here of electrons, and similarly Jp appears in the continuity equation for holes. The electron and hole concentrations appear in the equation for Jn as well as in the Gauss's law and in the continuity equations. You can see the carrier concentration appears here. So, this is how one can see that the 5 equations here are coupled. This equation E equal to minus grad psi stands out of this group, because after you have solved for the electron concentration, hole concentration, the electron and hole current densities and the electric field, one can easily use this equation to get the potential drop. So therefore, in device analysis one uses these 5 equations and one works with these 5 equations, and only after working with these 5 equations, if necessary, one uses this equation. Now you would recall that we had said earlier that the 6 drift diffusion equations can be reduced to 3 equations, 3 coupled equations in electron concentration, hole concentration and potential. Now this form in which you have 3 coupled equations is suitable for numerical simulation of devices. However, the equation, each of the equations in this 3 coupled equations is fairly lengthy. It contains many terms. You can see that very easily. You would have done the assignment, because when you take a divergence of Jn, actually you will have to differentiate each of these terms with respect to x, and further the diffusion coefficient and mobility will have to be assumed to be constant, otherwise each of the terms here will have to be differentiated according to the product rule and you will get many terms in the equations. So this form of equation, in the 3 coupled equation form, this is suitable for numerical simulation but not for analysis. For analytical approach one uses the equations separately. So it is easier to use each of these 6 equations separately, okay, and analyze. So 6 simple equations is more suitable for analysis than 3 complicated equations. 3 complicated equations, however, are suitable for numerical simulation, because there the computer can easily solve any complicated equation. It is more important to reduce the number of coupled equations in computer simulations. So the first step of derivation using this drift diffusion model would be a qualitative analysis, and this will be reflected in the sketch of electron concentration, hole concentration, electron current density, hole current density, electric field, potential versus x and t. The next step would be approximations of the 5 coupled drift diffusion equations based on qualitative insight. So the 5 equations are those within this boundary. The third step is reduction of the 5 approximated equations and the 6th equation to a single equation defining the characteristic time or length. So the 6th equation is this equation here. The 4th step is solution of the equation and interpretation of the time or length. And finally the 5th step is testing or validation of the approximations made. So we shall be using these 5 steps to derive the characteristic times and lengths based on the drift diffusion model. Let us take the first characteristic time, that is the minority carrier lifetime. This time is related to relaxation of small disturbance in excess electron hole pair concentration. Let us consider a physical situation. Suppose you have a semiconductor sample that is thin enough so that you are able to generate electron hole pairs, excess electron hole pairs uniformly throughout the device volume. Let us say this is a situation for t less than or equal to 0. So you have created excess electron hole pairs within a device volume, and at t equal to 0 you are switching off the source, that is the light which is creating electron hole pairs. Then what is going to happen? So you will find that progressively the electrons and holes will recombine and the semiconductor will return to equilibrium. Now what is the time that it will take to do so? So we shall show that this time, assuming an n-type semiconductor, the time to return to equilibrium would be about 3 times the lifetime of holes or minority carrier lifetime. Thus, if you want to describe this relaxation of excess carriers to equilibrium, then the characteristic time would be the minority carrier lifetime. Let us derive this characteristic time. Now first we should put down the conditions of this situation. So first you have a uniform semiconductor, then the excess electron hole pair concentration is uniform throughout the device volume at all instants of time. The generation rate, the excess generation rate G is switched off at t equal to 0, and finally we assume that the injection level is low, that is, excess minority carrier concentration is less than 1/10 of the equilibrium majority carrier concentration. Now excess minority carrier concentration would also be the same as excess majority carrier concentration in this case. So we can say that low level means the excess carrier concentration is less than 1/10 of the equilibrium majority carrier concentration. Now this is the statement of the small disturbance. So what do we mean by saying the disturbance is small? So this is the condition. So under this condition only the characteristic time that we derive will be valid. Now let us convert our preliminary understanding into graphs of, so here the G is switched off, so this is what is the graph of the generation rate as a function of x and t. So generation rate is uniform throughout the entire volume, that is our assumption, and it is switched off. So at t equal to 0 the generation rate abruptly falls to 0. It really does not matter how the generation rate was varying for t less than 0, right. All that it matters to us is that this generation rate was switched off at t equal to 0, and at t equal to 0 therefore there was some excess carrier concentration, and that excess carrier concentration is returning to equilibrium. So here we have plotted the excess hole concentration, which is the same as excess electron concentration in this case. So the initial value of the excess hole concentration is denoted as capital delta into P, whereas the lowercase delta is used for time varying excess carrier concentration. Now we shall show that the defining differential equation would turn out to be a simple differential equation of this sort. So dou by dou t of delta p is equal to minus of delta p by tau. Now we are talking in terms of minority carriers here. We can always write a similar equation for majority carriers by replacing delta p by delta n, because here delta p is equal to delta n. The boundary conditions to solve this defining differential equation would be the excess carrier concentration at any x for t equal to 0 is delta p. So for any x it is the same because conditions are uniform. Now let us derive the defining differential equation. So the first step is qualitative sketch of these quantities n, p, jn, jp, e and psi versus x and t. So let us say here we are plotting as a function of x, okay. So this would be at any t, at any instant of time, and we will also plot as a function of time for any x. Now first condition was the semiconductor is uniform. This means, for example, that the doping level is the same throughout the device volume. So this is shown here. So, I can say the N naught is Nd plus approximately, because we can neglect the contribution of minority carriers here. So, equilibrium majority carrier concentration, it is uniform. Now, equilibrium hole concentration also would be uniform. So, one can sketch that also. Now, if I want to show both equilibrium majority and minority carrier concentration, then I have to use a log scale. Okay? If I use a linear scale, then I should show a break. So, this could be P naught. Now, another condition that is given to us is that the generation rate is suddenly switched off. So, this is the picture for G as a function of time. Now, let us proceed further. What happens to the electron concentration and hole concentration? So, since conditions are uniform, the electron concentration is something like this, and the hole concentration also is uniform. So, here let us use a log scale to show both electron and hole concentrations. Now, on a log scale, because the injection level is low, I can say the N is approximately equal to N naught, and so this line would be the same as the equilibrium condition line. On the other hand, P, however, will be greatly disturbed as compared to the equilibrium picture. So, in fact, the P here would be approximately equal to delta P, because the delta P would be much more than P naught. So, this is a log scale. Supposing I sketch the excess carrier concentration as a function of x. That would also be uniform throughout. I can show this on a linear scale, and everywhere the excess hole concentration would be equal to excess electron concentration, because conditions are uniform. If you do this as a function of time, then the picture would be like this. The electron concentration would appear not to be changing on a log scale, because the injection level is low. So, the majority carrier concentration could be shown just the same approximately. The minority carrier concentration, however, will change from delta P to the equilibrium value. So, this is delta P and this is P naught. This is on a log scale. If I sketch the excess carrier concentration, that I can do on the linear scale. So, that is in fact shown by this difference here. The excess electron concentration is also the same, however, since it is a log scale, the majority carrier concentration does not appear to be disturbed very much. That is why this looks like an almost constant line. So, we now plot under for a linear scale, so it would look something like this. So, this is delta P and it will be equal to delta N. That is this point, and this is equal to delta N. Next, we need to sketch Jn and Jp. So, like we are sketching N and P on the same graph, delta P, delta N on the same graph, we should try to sketch Jn and Jp on the same graph. So now what would Jn and Jp depend on? If the carrier concentrations are uniform throughout the volume, you know that there is no diffusion current, but Jn and Jp can contain drift current also. Now how do you know whether there is a drift current or not? You need to know whether there is an electric field. So as of now, unless we know the electric field, we cannot plot Jn and Jp. So let us leave this for the present, move to the electric field. Now how do you plot the electric field? The electric field can be plotted if you know the space charge and boundary conditions of the electric field. So what is the space charge? So if I first try to sketch the space charge, that can be done based on the information about electrons and holes. So the space charge is q times p plus nd plus minus n for an n-type semiconductor. That is what we are assuming. Now since delta p is equal to delta n, therefore delta p will cancel delta n when I put here in this expression. So if I put p as p naught plus delta p and this n as n naught plus delta n, we know that p naught plus nd plus minus n naught is 0 because the semiconductor under equilibrium is space charge neutral, and since delta p is equal to delta n, therefore even under non-equilibrium conditions the space charge is 0. So here it is just a 0 line for the space charge. Now if space charge is not there, you know the electric field should be constant by the Gauss law, but there is no electric field either at the left end or at the right end. There are no surface charges, nor have you applied any electric field, therefore the electric field is 0. So since the electric field is 0, you know that electron and hole currents are also 0. Okay, so here all these lines will be just the x-axis. Psi, since there is no electric field, okay, the potential is not changing, we can assume the potential to be 0 everywhere. Now one can similarly plot this as a function of time. It is a trivial exercise because all these are 0, so the corresponding graphs here would all be the 0 lines. Okay, this is trivial. So now this is our qualitative analysis. Okay, we have understood what is happening to each of the quantities of the drift diffusion model, namely the electron concentration, the hole concentration, the electron current density, hole current density, electric field and potential. Okay, now we have not yet used the equations as such. Qualitatively reasoning, we have got this information. Now this background is very important to actually solve the equations. So one should not rush into solving the equations. One must first do this exercise for every problem that you encounter, and we shall be doing this for every device that we analyze, every situation that we analyze. So our next step would be approximations of the 5 coupled drift diffusion equations based on qualitative insight. Now these are the 5 equations which are circled here under this within this red curve. So we bother about the approximations for these because these are coupled. We really have to decouple them or simplify them or eliminate some of them. Now since the semiconductor is uniform and excess carrier concentration also is uniform, space charge is 0. So the space charge goes out of the picture, delta n equal to delta p. This charge neutrality condition is a very useful condition, as we shall see. The great achievement, the great result that you get out of the charge neutrality condition is that you need to solve only one of the 2 equations, 2 pairs of equations. So you need to solve the current density and the continuity equation for electron or for holes, this pair for holes. So two equations are going out of the picture. Now in this case we have removed the equation for the majority carriers. Okay, as we will see, often it will turn out to be easier to solve the equations for minority carriers. So if you have a choice of either solving the pair of equations for electrons, the current density continuity pair for electrons, or for holes, then you decide the type of the semiconductor, and based on the type of the semiconductor choose the pair for minority carriers. This point will become clearer as we proceed further and consider other characteristic times, such as for example the diffusion length. Let us see what other approximations are allowed because of the charge neutrality condition. Since excess electrons and holes are equal in concentration, the diffusion currents drop out. Since rho is 0, we have shown that electric field is 0, and therefore the drift terms drop out. Since the whole current itself is 0, the divergence term of the continuity equation of interest drops out. Now we have switched off the G, okay, and therefore for t greater than 0 this term does not enter into the picture. Now we have removed this E equal to minus grad psi, because actually there is no electric field, so we do not need this. This is not really a consequence of the switching off of G, it is a consequence of the E becoming 0. Now finally low level conditions. So what implication does this have? So it is because of low level conditions that the time constant tau entering in this term here is independent of the excess carrier concentration. So you would recall from the discussion in the previous module about the lifetime that under low level conditions, independent of the mechanism of recombination, whether it is Shockley-Reed-Hall recombination or thermal recombination or the Auger recombination or the radiative recombination, under low level conditions the lifetime is constant independent of excess carrier concentration. If the time constant is dependent on excess carrier concentration, then the differential equation would become a little bit more complex. The third step is reduction of the approximated equations to the equation defining the characteristic time. Now this is straightforward, because all that you need to do is just pick up this continuity equation for holes. So dou p by dou t is equal to minus delta by tau. So that is the equation. Now here on the left hand side you have dou delta p by dou t instead of dou p by dou t, because p is equal to delta p plus p naught, and we know that dou by dou t of p naught is 0. So therefore dou by dou t of p is dou by dou t of delta p. Next step is solution of the equation and interpretation of the times, and finally fifth step is testing or validation of the approximations made. Now validation is not much of an issue for our situation, because whatever simplifications we have done are a consequence of the conditions assumed for the situation. So we have really not made any approximations that are likely to be incorrect or anything like that. So we straight away go to the solution of the equation and interpretation of the time. The solution of this equation is an exponential that is shown here, and the carrier concentration decays exponentially from the initial value to the equilibrium value. Now from the properties of the exponential, you know that the exponential can be assumed to be almost died out if the duration is 3 times the time constant that enters into the exponential. So this time constant tau is lifetime of holes, tau p. So here the value would be less than 5% of the value here if you use the factor 3. Okay. Now that is the reason for using the factor 3. So whenever you find that the disturbance has reduced to less than 5% of its initial value, then you say the disturbance has almost died out. Now let us do a similar thing for another time constant, that is the dielectric relaxation time. The dielectric relaxation time is associated with relaxation of small disturbance in space charge. First let us describe the situation. So you have an n-type semiconductor in which you are injecting only one polarity of carriers. Let us say we are injecting majority carriers. So we shall consider the injection of majority carriers and minority carriers separately, right. First let us discuss the case in which we inject majority carriers. We will also assume that the majority carriers that are injected are uniform throughout the volume. So in this case for n-type semiconductor you have injected electrons. Now what is going to happen? So as shown here, the volume concentration of the excess electrons will decay to 0. So what is going to happen is the electrons are going to all move to the surface. Now since this is a one dimensional situation we are assuming, the electrons move to either the right surface or the left surface, right. So we are not shown any electrons on this horizontal surfaces because our situation is one dimensional. If it is a 3-dimensional volume, then you must consider the mobile carriers to move to the surface of the 3-dimensional volume. That is what will happen. Okay. Now we need to explain why does this happen, how does this happen, right, and we need to get an equation for this return of space charge to neutrality condition. So please note, space charge here is 0, but surface charge is not 0. So essentially what is happening is the space charge which was present at t equal to 0 is converting itself to a surface charge. So the situation here is that semiconductor is uniform and the injection of majority carriers is also uniform, and only majority carriers are injected, there are no minority carriers injected here. So this is not like electron hole pair injection, right, it is only electron injection, and also the excess electron concentration is small so that low level conditions prevail. So in terms of graphs, what we shall observe is the excess electron concentration decays to 0, the volume concentration decays to 0, it is converting into surface concentration, but volume concentration goes to 0 in a time that is about 3 times the time constant, namely the dielectric relaxation time, or the space charge decays to 0 in the same time. Now we will show that the defining differential equation would be of the similar form to that we just discussed, namely it will be a first order differential equation, okay, in time. So this would be given by dou rho by dou t, here rho is the space charge, equal to minus of rho by the dielectric relaxation time, which is given by epsilon s, that is the dielectric the permittivity of the semiconductor divided by the conductivity of the semiconductor. So we will have to show this. The boundary conditions in this case are the space charge for all x is the same because it is uniform condition, at t equal to 0 it is equal to minus q times the excess electron concentration that is injected. Now let us explain how this decay will happen. So again, to derive the defining differential equation, we will first do a qualitative analysis and sketch these quantities as a function of x and t. So, as soon as we inject electrons like this, an electric field is going to be set up. So, from the source from where these electrons came, an electric field would come, and each of these electrons would terminate an electric field line in this manner. So, if it is a volume, then the electric field would be something like this, okay, terminating on each of these charges. So, we will look at our one dimensional situation. Now, what is the consequence of this electric field coming here and terminating on the charge? Now, since this charge that we have injected is mobile, it will move in this direction, right. So, the electric field that has been created as a consequence of the space charge itself will try to drive the electrons either to this side or to this side. Now, this is the reason why ultimately the process stops only when the electrons move to the surface, because thereafter the picture would be something like this. So, the electrons can't move out of the surface and they will be held to the surface by the electric field, okay, and now the process will stop. So, that is how the space charge gets neutralized and converts into a surface charge. Now, let us look at things in detail and plot the various things the way we did earlier for the case of minority carrier lifetime. So, we are going to follow a similar approach. So, here again we have a uniformly doped semiconductor. So, your doping is uniform, okay. So, this is at any t as a function of x, and this is at any x as a function of t. So, let us start with electron and hole concentrations. So, the electron concentration, now we will use a linear scale, because otherwise we will not be able to show any variation of majority carrier concentration at all. We are assuming low injection level, whereas actually we have injected majority carriers, right, and it is their variation that we want to see. So, I am going to use a linear scale and I am going to show a cut. So, at any t your electron concentration would be something like this, n naught plus delta n. But since we are not injected any holes, the hole concentration would be just p naught. So, this is n and p as a function of x. Now, what about n and p as a function of time at any x? So, let us talk about since the carrier concentration is uniform at any x, we will see the same picture. So, the electron concentration is converting itself into a surface charge and the volume concentration is dying out. So, it would be like this. So, this is n naught plus delta n is this point, this is n naught. P naught, however, P no change, because we are not injecting any holes. Now, note that this electric field will act on the holes also. So, when the electric field is moving the mobile electrons to the surface, will they not act on the holes? Yes, they will act on the holes also. However, the disturbance of the holes would be really very small, right. So, it is going to be mostly the electrons that are going to be affected by the field, because they are in very high concentration, and the drift current, you know, that is causing the volume concentration of electrons to move to the surface will be several orders of magnitude more than the drift current of holes, because holes are minority carriers. So we really don't bother about the change in the hole concentration. Now Jn and Jp as a function of x. Again, if you want to know Jn and Jp, I should know the electric field. The carrier concentration is uniform throughout the volume, therefore there is no diffusion current. So there is drift current because there is an electric field. But what is the variation of the electric field? Unless we know that, we cannot plot this. So let us move to the electric field. Now for doing the electric field as a function of x, we need to know the space charge, rho versus x. Now the space charge at any x is uniform and it is given by minus q times excess electron concentration. So the space charge uniform and negative, and therefore the electric field picture as a function of x, if you have uniform space charge, dE by dx according to Gauss law is constant. So either the field picture will be linearly varying like this or like this. Now which is the correct one? Well, you can look at the picture here. You can see that towards the right surface the field is inside. So this means the field is in the negative x direction here at this surface, and at this surface it is in the positive x direction. So the picture would be something like this. So this is E versus x, linearly varying. Now because E is varying like this, the current because of this also will have similar variation. So this is suppose Jn, Jp we really cannot show on the same scale because hole concentration is orders of magnitude less than electron concentration. So really Jp is negligible. So we cannot show Jp. So we will just say Jp very small. And finally, if you want to sketch the potential based on this, so as you move in this direction, your electric field, if it is from left to right, your potential decreases, right? And then this electric field is from right to left, as you move against this it increases. So therefore your potential picture would be something like this. So that is your picture for the electron current, hole current, electric field and potential, right? So what is happening is at any t your current is like this, it is 0 at the center, and here it is positive and here it is negative because you see the electrons are moving to the left because of the field, therefore the current is to the right, and here the electrons are moving to the right, therefore the current is to the left. That is what it shows. So at the center you have almost no current, but the current increases as you move away from the center. So what is going to happen is, as a function of time, this current is going to drop like this. So this line is going to change like that. So at any other time if I want to draw this line, it would be something like this, and ultimately it will become flat. Let us complete quickly the picture as a function of time. So since the current will be proportional to the carrier concentration and the electric field, okay, at any x you have some electric field here. Now electric field is also dropping, right? Carrier constant also is dropping, so the current Jn would be something like this as a function of time. Jp we really do not show because it is really very, very small. If you want to plot the electric field, that would also fall at any x. So let us say if I take the x here, we are taking an x somewhere here. Similarly, this electron current has been shown to be positive, which means the x is somewhere here, right? If you take x here, the electron current would be negative. So let us say this is the place x1. So this is at x1, and similarly this electric field is as a function of t. Space charge. which is actually of our interest. Space charge, however, is negative everywhere. So let us move this line up. And space charge would decay like this, should be on the negative side. So this is minus q delta n, that is this value. This electric field, if you want to convert, if you want to write in terms of this, it would be dependent on this multiplied by the volume and then divided by the epsilon s. As a function of time, the potential again at any x, so the region becomes neutral and the potential inside the region falls. So this is psi as a function of time. Now the next step to do would be to approximate the 5 coupled drift diffusion equations based on qualitative insight. Since we have come towards the end of the lecture, we will postpone this discussion to the next class and we will summarize what we have achieved in this lecture. So in this lecture we began a discussion of the characteristic lengths and times. These are very useful metrics while analyzing situations related to semiconductor devices. They allow us to decide what kind of approximations will hold in which situation. We discussed the characteristic lengths and times associated with carriers in random thermal motion under equilibrium. Then we outlined a procedure for deriving the characteristic lengths and times based on the drift diffusion model, wherein we said first we should do the qualitative analysis and express it in terms of graphs of n, p, jn, jp, e and psi as a function of x and t. Then we should use this qualitative insight to approximate the equations to decide what equations can be eliminated and which terms can be simplified. In particular, we saw that if you can make the quasi neutrality or charge neutrality assumption, then you need to solve only one pair of equations, current density continuity equations, right, either that of electrons or that of holes. So one pair of equations is eliminated by the charge neutrality condition. Then we solve or reduce the approximated equations to a single defining equation for the characteristic lengths or time. We applied this procedure to derive the characteristic time associated with decay of excess electron hole pairs to equilibrium in a uniform semiconductor, and then we began a discussion of the decay of excess charge or space charge to charge neutrality condition, right, and specifically we considered the instance of space charge neutralization to charge neutrality condition when you inject excess majority carriers into a semiconductor sample. So we will complete this discussion of the decay of space charge when you inject majority carriers, and we will repeat a similar exercise for minority carrier injection also. This we will do in the next class.